My name is George Collar and I'm with the Statistical Design Institute. In this tutorial we would like to continue our discussion of the Apogee tool set that is within the SDI Tools version 3 software. In this discussion we'll be focusing on primarily the statistical allocation techniques that are included within this tool. Our emphasis will be on performing a design analysis and more specifically an allocation to support specified design requirements. In the example that we've discussed in previous tutorials regarding the design of this cylinder that would be used as a fluid reservoir in a product, is that we had a specified height, outside diameter, wall thickness, and material density, and that we had the indicated nominal values and tolerances specified for each one of these. Now the objective is that if we produce this design due to these parameter values, that we would be able to achieve a particular inside volume and cylinder mass that would satisfy specified design specifications or requirements for this design. So we've analyzed the design using the analytical relationships, and we've also included in our analysis the statistical properties of the height, the outside diameter, the wall thickness, and the material density parameter conditions. So these have been included. We did the analysis, and if you remember from the prior sessions, we did a sensitivity analysis and a Monte Carlo analysis, and from those we were able to predict the probability of non-compliance for the cylinder weight, which we determined to be approximately 22%, and for the inside volume, which was approximately 8%, and determined that this design is probably marginal at best in terms of its quality and its producibility. And what we'd like to do is have a design that would give us probability of non-compliances for both the cylinder weight and the inside volume of 1% or less. So rather than doing a complete redesign, what we would like to do is determine if we could reallocate the tolerances, the uncertainties, for the key design parameters in order to support these specified probability of non-compliance objectives. So let's go to our worksheet for this design, and let's see if we can look at a way that we can use the Apogee tool to support the allocation of tolerances in order to meet our P&C objectives of 1%. Okay, so we're back to our worksheet that we set up before, and we've opened this in Microsoft Excel, and I have previously opened the Apogee tool set, which is included in this case in the add-in ribbon, and we can use either the Apogee drop-down menu to access various functions, or we can use the toolbar that's available to us. So in the previous discussion we defined, remember, each one of our X's in this with their statistical properties. We've identified our Y responses that we're analyzing, and we had performed a sensitivity analysis for both the inside volume and for the cylinder weight. Okay, so now then let's go back to our cylinder equations worksheet, and let's look at what we could do to assign tolerances to each one of these parameters in order to meet a specified performance objectives for inside volume and cylinder weight. So it's very easy at this point with the setup that we've already performed. Is we can go to the Apogee toolbar, go to the allocation function, which is the one with the arrow pointing down, of allocating a response variation to the individual parameters. So we'll click this function. We will see the responses that are indicated here that we can do the allocation for. And since in our prior design we really had the most difficulty with cylinder weight, we could do both of these, but let's go ahead and just do the cylinder weight allocation at this time. We'll identify the parameters. The tool will automatically identify the parameters that will influence the variation on cylinder weight, and those are indicated here. We'll just click OK to accept those. And at this point we have created a cylinder weight allocation worksheet. So this is another worksheet within our workbook where our prior analyses have been included also. So this worksheet is automatically generated, and what we see here is that we've identified the response name, the location in cell C14 where this equation resides in our worksheet. The equation value, which is determined by plugging the mean values, the nominal values, into the equation for this condition. We see that what's indicated is the upper and lower spec limits for this design response, and then also the mean values for each one of these also. Okay, now then that's the response section or parameter section of the allocation worksheet. In the allocation section, what we have is where we can identify the standard deviation budget that would be used for this desired response that we're looking at. Now, this standard deviation budget of 27.29 is determined actually from what the response PNC is that we desire for this particular condition. So let me go back to the equations worksheet. We're looking at the cylinder weight, and if I look at the Y specification for this, where we had previously specified the lower spec limit and the upper spec limit, I've also included what the desired PNC would be. So in this case, a desired PNC of 1% or 0.01 is what's been included. So going back to the allocation worksheet, the response standard deviation that would be required in order to meet a response PNC of 0.01 has been determined to be 27.29. Okay. Now, in the allocation process, there are three techniques we can use to do the allocation. Do the allocation based on sensitivities of the individual parameters to the response variation. We could do it based on second derivatives, and in this case it would be based on the influence of the second derivatives or the nonlinear conditions of this equation to the response variation. Or we can do this based on relative cost, in which case we will provide numbers that would be related to the relative cost of controlling or maintaining or achieving each one of these conditions on our design parameters. So for this demonstration, we're going to do the sensitivities. The first partial derivatives are included here as part of our sensitivity result, and we see here that automatically we have allocated standard deviations that could be assigned for these parameters in order to achieve the response PNC of 0.01 with our response standard deviation of 27.9, which is what we had budgeted. So basically the tool has automatically done the allocation and given us a set of standard deviations to achieve the desired results. Also in the results section we have our parameter information. I've indicated of what the current variance contribution would be for these allocated standard deviations assigned to these mean values for each one of our parameters. We also have computed the mean shift contribution, and then using the allocated standard deviations we can determine what the assigned tolerances would be, assuming that these tolerances are symmetric about the mean values with the variation indicated by the allocated standard deviations, and then we can specify what the tolerance sigma rule would be that would be used to compute or convert the standard deviations into individual tolerances. So in this case, for this design, we can see that if we had a tolerance of about 3.2 for the height, of about 0.49 for the outside diameter, about 0.0001 for the wall thickness, and about 0.023 for the material density, that these tolerances would result in a design that would provide a PNC of about 1% for this case. Now then, this is only one of really about an infinite number of possible tolerance assignments that we could achieve or assign in order to achieve the desired response PNC. So if we want to go examine other tolerancing conditions, what I'm going to get you to do is notice the tolerance half widths, notice the allocated standard deviations, is that we can go adjust this standard deviation contrast, and what we can do is go through other possible conditions that would result in the tolerance assignments that would give us the response PNC of 0.01. So in all of these cases the response PNC is staying fixed, and we're looking at other tolerance conditions that would allow this to be achieved. Now in this tool, what we can do is look at really an infinite number of possibilities, but look at some unique conditions also. So in this case, with the standard deviation contrast at the high end of this bar, this slider bar, what we have are allocated standard deviations that are inversely proportional to the partial derivatives or the sensitivities. So in other words, if a parameter has a large sensitivity, that means small changes of this parameter would have big influences on the response. We see that the allocated standard deviation is very, very small and resulting in very tight tolerances on that parameter. However, if the sensitivity is very small, then we see that the allocated standard deviation is very large. So in this case, change of this parameter has a very small influence on variation of the response. And we see that we have then a large assigned tolerance as compared to the other parameters. Now another condition, or is it really what would happen is we start moving this slider bar towards the low end, is that really we're loosening this constraint and we're allowing more or less dependency upon the allocation drivers or the sensitivities in the final allocation of parameter values for this solution. And in fact, if we go ahead and slide this tolerance, this slider bar to the low end of the scale, all the way to the low end, we see that we get a unique tolerancing condition where all of the allocated standard deviations are equal, and depending on the tolerance sigma rule, we may have the equal assignment of tolerances to each one of the parameters also. So what we have now are really different conditions that you can explore for assigning tolerances for your design. And we see also that as we change the assignment of tolerances, that the resulting variance contribution changes also. So in this case, with equal standard deviations, we see that the wall thickness has a high contribution to the response variance. If we went to the high end of the scale, based on sensitivities, we now see that the wall thickness has a very low contribution to the variance of the response. And in fact, it turns out that there is another unique condition that we could arrive at, in which case all of the variance contributions could be equal, and the allocated standard deviations are set up so that they would have, each parameter would have an equal effect to the overall response variance. So with this tool, you can go in and really look at a variety of conditions that you would want to use for picking the individual assignments. Now one thing we could do is, if we assume that maybe material density is a condition that we may want to pay attention to initially, is that we can go in and let's just focus on this one parameter, and let's find maybe a standard deviation that we think would be achievable for this result. And actually, I tell you what, let's do is let's go pick a material density standard deviation that would result in a tolerance half width of 0.2. So by selecting a cell here on the material density line, we can go up and assign the parameter standard deviation. Let me assign the standard deviation so I'd have a tolerance of 0.2, just a value that I selected. Click the OK button. We see that we've determined the allocated standard deviation for that, and now then this parameter will be fixed, and all of the other parameters can now be examined in terms of tolerance assignments or standard deviation assignments or allocations that would allow me to support my close to 0.01 PNC, fixing the material density, but now having control of adjusting the standard deviations across the other. So now we can go and look at other conditions that might result in candidate tolerances for these. Maybe when I find a condition that I like, in fact in our original design we have had a wall thickness of 0.005. So let me see if I can get the result that would do that. Just selecting some values here. Actually it was 0.0057 or 0.0006 is about what we had. Let me see if I can come to a condition that would be about that. So if I wanted to maintain that same condition, so here is an assignment that is very close to what we had in our original design from the prior tutorial sessions. So now then, if I like this assignment of say approximately 0.006 for this condition, then I can check the box. We'll make this a keep parameter, and now then I can assign tolerances across the other two as appropriate in order to meet my design conditions. Okay, so I could go with the equal standard deviation or equal tolerance condition. I could go with the equal contribution to variance condition and see what that assignment would be, or do the assignment strictly based on sensitivities or anything in between. So a lot of different options here that you can use in this tool, and then once you've determined the assignment that you want, you could go click the apply changes, move those conditions back to the definitions that we had our original worksheet, and now you've allocated tolerances for this design and variations based on a desired response condition. So it really takes away a lot of the trial and error, where if you change one tolerance it has kind of influence on the response result. Now you can do this in a controlled fashion and really make your tolerance assignments more productive and more beneficial to achieving a desired result. Okay. So going back to our discussion, we now have really changed our tolerance condition. We have a set of results that now will provide response PNCs of less than 1%. We only did this for the cylinder weight, but you can go back and do the same thing for the inside volume, and then you'd have to coordinate between these two responses to get a compliant result based on these conditions. So in this tutorial, let me go back. We've completed this allocation. We've completed a demonstration of the allocation function within the SDI Tools Apogee software. If you do have questions about this tool, the technique itself, feel free to send me an email, give me a call, and I'll discuss it with you. If you'd like to download the SDI Tools, you can go to stat-design.com, go to one of the links for the download the SDI Tools, install it, and on your initial installation you'll have a 7-day trial capability of the complete tool set. And if you wish to extend that license with either a temporary or permanent license, then give us a call and we'll discuss with you licensing arrangements for purchasing this tool. So thank you very much, and there will be other tutorial sessions discussing other capabilities within the Apogee tool set. So I welcome you to take advantage of those also. So thank you and goodbye.